this let will not recursively define x. So the x on the right hand side here must refer to anything above it. Okay?
That's Haskell or OCaml?
OCaml. For OCaml, the let is not recursive by default. Okay? The equivalence in Haskell is the equivalence. If it's a Haskell code, the equivalence in OCaml is like rect. Now this x is recursive. You can use it within here, whether or not it's correct. Whether or not this leads to a useful result or not, this is basically equivalent to the Haskell let. Okay. There is actually an advantage of a non-recursive let. The advantage is you can do shadowing.
What's shadowing?
You basically just have a chain of this. So let's say I have a very long operation. Start with x. Then I have a 10. I want to do +1. And then I do this. Right? So this one in. Okay? So I start with 1, then I do 1 + 1, which is 2, and then I do 2 times 2, which is 4. Okay? But I don't need to describe other names. Okay? If there's if everything is recursive by default, then I need to do x here, this one is y, this one is z. Okay? So I can reduce the what we call the pollution of namespace by doing the shadowing. Because everything is strict, the I/O itself can be impure by default. You don't even need to have monad. Okay, and then the OOP feature. Okay, so this is the first part. This is what I said. Let binding is not recursive, so here you have 1 minus 3. Okay. If you want recursion, you need to say let rect. So if you want to define the factorial function, then it's let rect factorial. Okay? Then you say x equals to if something. Okay? So if x equals to 0 is 1, else something. Then you can use the factorial. You can call factorial x minus 1 over here. I think x times factorial x minus 1 can be called over here. If you forget the rect, then this one fails. Okay? So it kind of forces you to know whether you want the recursion or not. And it's actually mutually recursive. So this is a nice example. F here can call G, G can call F. Okay, but to get the mutual recursion, you have to have N. So the general notation will be something like let rect, so F something, and G something, and so on. Okay? So within this dot dot dot, or actually wait. G dot dot dot, so equals to dot dot dot. Okay, and then this dot dot dot. So within this dot 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 of the body, you can call F G freely. Okay. If you forget the rect, then G can call F, but F cannot call G. Or actually, if you do this, and they each cannot call each other, I believe. Alright? The first part here is the nice one because it supports the said shadowing. This is what we mean by shadowing. Okay? You don't have to keep on creating new variable names again and again. Eventually, you will be out of short variable names. Then you have to use longer names. Type. So type variable has this notation, and I'm not sure if you can see here, but that basically corresponds to this button, the one next to 1. But actually, that's just minor things, right? Because you will not be writing. I don't think you'll be writing that one. Because OCaml has a type inference. List, like this, is written in a postfix thing. List is your functor. Okay. So it's kind of like your type application, but it is written in a postfix format. So it's a list of A. Kind of make things slightly difficult to read. This one means it's a list of A. This is the functor, this is the type. That's in Haskell, it's prefix. In OCaml, it's a list of A. Okay. Again, similar to, so if you look at it similar to Haskell, it has the curry automatically. Okay. So like Haskell, if you only specify up to this argument, then the rest is you have a function, you return a function, and then you can apply another argument. So this one is also currying by default. Unlike Haskell, in the strict evaluation, there's no, the default one is not lazy, but the order can be random. And this is, in a pure setting is irrelevant. It doesn't really matter. Right? Because in a pure setting, whether I evaluate E1 first or E2 first, the result will give me the same thing. But because OCaml has an impure part, then the order can matter. If you really need to know the ordering, then you use lat. Lat is always evaluated from top to bottom. So you will evaluate this one first, and then you will evaluate this, and then you will do this. Okay? So any questions? Lat, actually there's this very nice thing about lat. It is a sequence of lat kind of makes things imperative. Because if I have a program in C, let's say you have y equals to x plus 1, and then you say the x, that's it. You start with a declaration where x starts with 1, and then x equals to x plus 1, and then you say that y is equals to x times 2. You can always convert this to lat. Lots of lat. So you let x equals to 1 in, so the semicolon becomes in, and then you say let x equals to x plus 1 in, let y equals to x times 2 in. Your last result is just going to be the return. Okay? So the last value that you evaluated, in this case y, that will be just your return value. So you can always convert the imperative style into sequence of lats, because the ordering here is fixed. You start from top to bottom. Okay? So something to cheat if you want to write things in imperative format. But obviously there's not really a while. There's if, but there's not really while loop. So while loop, you need to do something else to simulate that. There's another way to force an evaluation. You can use this second. Okay, then x will be strictly evaluated first. Right? So, yeah, so this is something. Oh, this is for Haskell, sorry. This is not for OCaml. OCaml is always strict, but in Haskell, if you want to do the strict evaluation, is this. Strict means it's not lazy, okay? Or what we call an eager evaluation. There is, however, a lazy module. So, how? Yeah, one of the wheel is gone. How do you create a lazy from a non-lazy? So I'm not sure if Prof. Chin actually talked about this, but when you have a function, let's say f, then you have, let's say x, right? Then you have x plus y. Let's say this is what you want to do. Now plus is basically just a function, so you have plus x, y, or something. The only difference between a lazy and an eager evaluation is that whether this one is a value or a function. Okay? So if this one is a lambda that contains nothing, and it gives me x, I wrap all the x into this, then what I get is a lazy evaluation. Because I will not evaluate this x unless it is called. So when do I call? Well, if I really need the value over here, then what I do is x, apply, or apply this, call this function. And because this is a function, I can just call. So this is the only difference between a lazy and a non-lazy evaluation. In a lazy setting, all the variable is wrapped within a function. That function has a single call, which is, let's call it apply, right? So until you call apply, the value is unevaluated. That's the main difference. Okay? So if you think about this function, or let's say plus x1, right? So if everything is lazy, at this particular point, x is basically a lambda that returns x. Whatever x is. Okay, if I call f2, this one is a function that if I call, I get this. This is my x. Right? So now this x is just this. 1 here is just a lambda that if I invoke, gives me 1. If I really need the result, right? So when I return, my return value is also a lambda. A lambda that contains another lambda plus, so this, I call this, and then I also call this, but this is a lambda. Right? So that's what a lazy evaluation is in the end. Every variable is a function. It's a function that is wrapping a value. Okay, so if you apply the function, if you call that function, then you get the value, then you can add. You can do the normal addition. If I really need the result of this return, then I can just invoke this value, this function. Right? Which means that if that's what we mean by lazy, we can create lazy as a functor. As a functor that do the wrapping. So lazy now just becomes a functor. And this is the meaning of the functor. Right? So force there, this forcing, is basically calling this function. Okay, so it's not exactly the pure function like this, because in a pure function like this, whenever you call force, you will need to keep on forcing things. Right? In some way, for Haskell at least, I think, once you force something into a value, then you don't have to evaluate it anymore. Okay? There is the term for that, and it's called memoization. So this one, after this function is evaluated, every occurrences of this function can be replaced with just the value that you compute. So you don't have to keep on computing this again and again. That gives you some kind of speed advantage over a pure lazy. Okay, so now we look at the impure part, the imperative part. So far we just look at pure functions. Some real world performance, some real world program will definitely depends on something that is impure. Okay? And the reason for that is because if you need a value, then there's no point in keep on computing that value again and again. So it's things like this. Once you have computed this, then might as well store the value. But if you store the value, that means there is an impure part. Okay? So because there is an impure part, then the compromise is basically, yeah, so mostly it will be pure, but I can give you something, if you know what to do, I'm giving you something that if you really know what to do, you can use an impure part. But it's your own choice. If you make a mistake, it's your fault. Okay? So that's what the programmer, what the developer of this programming language basically say. Everything else will be mostly pure, but I'm giving you this option. If you screw up, that's your fault. Okay? So yeah, the first impure part is what we call a mutable reference. This is how you create a mutable reference. So there is a keyword called ref. Now ref here is very, very special because it creates a box. Okay, so if you talk in terms of the functor, it is the box. So if in a normal way you let x equals to 10, right? So everywhere within this, x will have a value of 10. But, okay, so this one within here, x equals to 10. If you create the box here, so let ptr equals to ref 10 in something. Now if you do this, you do not know whether it contains 10 or it contains 11, depending on what you do in the middle. Okay, so that's the impure part because it is a reference. What it will basically create is that there is this box that currently contains 10. And ptr is the way to access this. So how do we access? Well, if I want to look at the value, I can do a back. If I use an exclamation mark, I'm basically looking at the value here. Give me 10. If I want to modify the value, then what I do is, I say that ptr, this is the walrus operation, I can say 2. I open the box, I put 2 here. Okay. So now, if I do something with ptr here, so that at this point ptr is 2. Okay, so that's basically the impure part. It's kind of like you have a global variable, and the global variable, the value can change depending on where, depending on all the previous operations that has been done to it. So here is the disadvantage of the mutable reference in the impure part. The disadvantage is that if I am giving you this particular program, will this give me true or false? Okay? So let's say somewhere above there's a ptr ref 10. Will this give me true or false? Okay? The answer is you don't know, because it depends on what happens over here. So if you just look at parts of the program, you do not know whether it's going to give you to reason about this, you need to look at other parts of the program. That's the disadvantage of the impure. But if I say this, then x equals greater than 0 is, x is always giving me the value 10. Alright? Okay, so to make it concrete, okay, so let's say make it concrete. Let's further restrict this. I have PTR greater than 10. What I'm saying here is that this is the nearest definition. This is the nearest definition of PTR. In the middle, there's no redefinition of PTR. So similar to this, there's no redefinition of x in the middle. But it calls a function g that I'm giving PTR. Alright? So whether this one is still greater than 0 or not depends on what this function g is doing. The function g can modify the value within the PTR. Right? And that's where the complication lies, because I do not know what the result of this is unless I know what this function g is doing. There's an interdependence between the parts of the code. But if I call g here with x, it doesn't matter what g is doing, x is still 10. Okay? So that's the advantage of a pure over impure. You look at any part of the program, you know that to reason about this, you just have to look at this component. For impure part, to reason about this, you need to look at g. You need to know what g is doing. Okay? But again, if you do minimal changes, like let's say you only use this feature sporadically, you don't use it everywhere, then most of the time you don't get into this problem. And if you really know what you're doing, then it actually helps a lot. So yeah, that's the basic of mutable reference. So ref is basically a function that takes a value and creates a container. Okay? You have a value, you put it inside the box. Then you can actually create, you can kind of think about the function of this, the dereferencing, as having a type of this, okay, and then yeah, and this one, the walrus, as again an operator that takes in the left part is this. The left part is a reference. So this is the left hand side. The right hand side is a value. And it gives you another ref. Okay, so this is the left hand side. This is the right hand side. And this is the result. Okay? You can think of it as something similar to that. And this is a type variable, so this one can be anything. You can have a reference to an integer, reference to a string, and so on. Okay, so this is what I said, the dereferencing. Yeah, this one actually is unit because it doesn't have a return value. So slightly wrong here. Should be unit. Unit means that there's no return value. In the context of Java and C, that is basically void. Okay? Like public static void main. Void, that means there's no return type. Unit here means that there's no return type. If you want to use the type checking mechanism, the type inference, and you want to say that this should be type checked completely, you need to say this. Because there's no return type, it's a unit. The way to specify that this must be a unit is to give this an empty bracket. Okay? So, I think there's a, like let's say this print n line. The print n line, doesn't return you anything. Right? If you want to take advantage of the, let me use, I haven't installed OCaml here. If you want to take advantage of the type inference, when you want to print line, you can print. Okay, so the meaning of this is basically you have a box here. The box contains an integer. Okay, so you dereference that. You open the box, you look at the value. The value is an integer. You convert from integer to string. So it's the string value of some kind of integer, and then you print that. Now, in OCaml, you can actually use this. Yes, I believe it's the semicolon. A single semicolon means that I can do the next operation. I can print another one. Okay, so semicolon is an operator. It is an operator that says do the left one first before you do the right. This is the right operand. Okay? But this one means that I don't care about type checking. Okay? Print and line can return me a value, and I don't care because I'm not going to use it. If you want if you want to check fully the type match, you need to use let here and say that the return value of this is a unit. Now, if you do this, and let's say you forget this, the print and line expects a string, but this one is a function that expects an integer. The type checking will not match because you will not get a unit. The type of a print and line, okay, the type of a print and line here will be string to unit. Okay, the type of this string of int will be int to string. Okay, when you try to connect the two here, you have a function where you're expecting a string. Right? So there can be a type error here, or at the end here, this one cannot be a unit. So yeah. So if you really want to do the type checking until the end, then you need to use this, saying that there is a unit type. So any questions so far? So that's dereferencing, that's updating the value. Actually, I think we should just stop here. This is basically about the implementation of the ref type. So it's going to take some time. So ref type is kind of implemented as this mutable field of record. So let's just stop here.
The next tutorial will be in
Prolog. Okay. I believe Benedict should have returned by then. Yeah, Benedict is on leave. Okay, so let's take attendance. I almost died again. Adi Kesama, Chan Wei Song, Chen Hu, Chua Jing Lee, Dai Wei, Fire,
I think it's like principles.
Si Wen, Si Wen here, Hong Jian Cheng, January, Lam Chi Chu,